Welcome to Chapter 7, the normal probability distribution. We're only going to do a couple sections in this chapter, and the first one is 7.1, the properties of the normal distribution. We have a number of learning objectives we're going to cover that you can see here, but we'll be going through them one at a time, so I'm not going to restate them. Use the uniform probability distribution. So what is this? Imagine that a friend of yours is always late. Let the random variable x represent the time from when you are supposed to meet your friend until he shows up. Suppose your friend could be on time. In this case, x would equal 0 because he shows up. There's no additional time after you were supposed to meet. Or up to 30 minutes late, where x would equal 30. X is the amount of time from when you are supposed to meet. With all equal intervals of time between x equals 0 and x equals 30 being equally likely. So what we're saying here is just that it's equally likely that he might show up 10 minutes late, or 12 minutes late, or 14 minutes late, or between 5 and 10, between 15 and 20. So as long as the intervals are equal amounts of time, they're equally likely. Okay, I just said that. The random variable x can be any value in the interval from 0 to 30, that is, 0 is less than or equal to x is less than or equal to 30. Because any two intervals of equal length between 0 and 30 inclusive are equally likely, the random variable x is said to follow a uniform probability distribution. Okay, so again, if the intervals of equal length, whatever your random variable is, are equally likely, the random variable follows a uniform probability distribution. A probability density function, known as a PDF, great, that's going to confuse us all, right, is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. The total area under the graph of the equation over all possible values of the random variable must equal 1. Okay, so this is kind of connecting to the idea of probability, right? That all the probabilities must add up to 1. And so the area under the graph must equal 1. The height of the graph must be greater than or equal to 0 for all possible values of the random variable. So this is just saying that the height of the graph is positive, okay? And it has to be positive or 0. It could be, it could be 0 probably at the extreme ends, okay? So the total area equals 1. The height of the graph has to be 0 or positive. The graph below illustrates the properties for the late example. So we can see the random variable is time, and we go from 0 to 30. And since the area has to be equal to 1, then the height of the graph has to be 1 over 30th, because width, 30, times height has to equal 1, so it has to be 1 over 30th. So the area of the rectangle is 1, and the graph is greater than, it's above the x-axis for all the values between x and 30. Because the area of the rectangle is height times width, and the width of the rectangle is 30, the height must be 1 over 30. Sorry, I'm restating that. The area under the graph of the density function over an interval represents the probability of observing a value of the random variable in that interval. So what this is saying is that if we looked at the area of the graph between 5 and 10, the area under that sector would give us the probability that someone would be between 5 and 10 minutes late. Okay? So here we're going to do a couple examples. What is the probability your friend will be between 10 and 20 minutes late? So again, what we're doing is we're shading the area between 10 and 20 on the x-axis and finding the area of this rectangle, and that will give us the probability for this interval. So the width of that rectangle is 10, 20 minus 10 is 10, and the height of the rectangle is 1 over 30. It's the same all the way across. So the area between 10 and 20 is height times width, or 1 over 30 times 10, which gives us 10 over 30, which is 1/3. So the probability our friend will be 10 to 20 minutes late is 1/3, or 33%. Let's look at the next question. It is 10 a.m. There is a 20% probability your friend will arrive within the next fill in the blank minutes. So we have to figure out how many minutes late that person can be, that there would be a 20% probability, okay? So again, remember the probability is equal to the area under that interval. So we know the height of the graph because it's 1 over 30 for everything. We know the area because that's given in the problem. Remember, the probability is the area. So the area equals 20%, or 0.2. And so we can do a simple algebra formula to find this. So if area equals height times width, and we're trying to find the width, right, because we know what the height is, then we divide both sides by h, and we get the width equals the area over height, or the area divided by height. Well, in the problem, the area, or the probability, is 0.2. The height is the same for everything, 1 over 30. So 0.2 divided by 1 over 30 equals 6, okay? So what this says is that there's a 20% probability your friend will arrive within the next 6 minutes, or by 10:06 a.m., because it is 10 now. So there's a 20% probability that your friend will arrive by 10:06. Okay? So you can see how this could help you figure out some probabilities when we have a continuous random variable. Our second objective is to graph a normal curve. Now, previously we learned how to do histograms, okay? In mathematics, a model is an equation, a table, or graph used to describe reality. The red curve, which are hard to see in here, in the first one you can see it kind of going up and through. The second one, if we didn't have such dark colors, it might work a little bit better. You can see there. And then the third one is really hard to see. But anyway, the red curves in the figures is a model called the normal curve, which is used to describe continuous random variables that are said to be normally distributed. Okay, normally distributed. A continuous random variable is normally distributed, or has a normal probability distribution, if its relative frequency histogram has the shape of a normal curve, or a bell curve. The points at x equals mu minus sigma, right, the mean minus 1 standard deviation, and mu plus sigma, or mean plus 1 standard deviation, are the inflection points, and you can see that on the graph here to the left, where the curvature of the graph changes, right? Remember, that's what an inflection point is. So at the top here we have a concave down, and when it hits the inflection point, it's now going concave up. Okay, think of like a spoon. The top of it's pointing down, but when you hit the inflection point, you turn the spoon over, and now the spoon is facing up, which is the direction you want if you're eating cereal and you don't want to be messy. The figures to the right show how mu, the mean, and sigma, the standard deviation, change the position, like in figure A, or the shape, as in figure B, of a normal curve. In figure A, increasing the mean from 0 to 3, it's hard to see these, caused the graph to shift 3 units to the right, but kept its shape, okay? That makes sense, right? Because the mean is the highest point of these graphs, and so if we're increasing it by 3, that means the x value has gone up by 3, which means we're moving along the x-axis 3 units to the right. In figure B, increasing the standard deviation from 1 to 2 causes the graph to become flatter and more spread out, right? So again, if we're making the standard deviation larger, then the graph is going to, that means that the area from the mean to that next point, each of those regions, is going to get fatter. And so, excuse me. Sorry, guys. And so it's going to become fatter or spread out. As you can see, the little blue graph there is further spread out. Why does it spread out? Because remember, it has to have the same area 1. Okay? State the properties of the normal curve. You remember this normal distribution from the empirical method, right? So we have 1 standard deviation gives us 68%. 2 standard deviation gives us, what is that, 68 plus 26, 94? Is that right? 26, 27. So 68 plus 27 is 95%. And then we go to the green is the 3 standard deviations. Okay. So let's look at those properties one by one. The graph is symmetric about its mean, mu, right? So that it's the same on both sides. When it's symmetric like that, the mean equals the median equals the mode, and the curve has a single peak, and the highest point occurs at the mean. It has inflection points at u plus or minus 1 standard deviation, the mean plus or minus 1 standard deviation. The area under the curve is equal to 1. We already talked about that. The area under the curve to the right of the mean equals the area to the left of the mean, which equals, each of those areas equals 1/2. So if the mean is splitting it exactly in the middle and the whole area is 1, then on each side it has to equal 1/2, right? Because it's splitting it directly in half, literally. As x increases without bound, and what we're talking here is getting larger and larger to the right, the graph approaches but never quite connects with the horizontal axis. This happens as well as the graph decreases without bound, getting smaller and smaller. It also approaches the horizontal axis. And we know that because that's the general description of a symmetric graph or a bell curve. And again, just a reminder from the empirical rule that 68% of the area is between the mean plus or minus 1 standard deviation. 95% of the area is between the mean plus or minus 2 standard deviations. And the mean, the area is approximately 99.7% of the area between the mean plus or minus 3 standard deviations. And again, this is just what we learned in the empirical rule in a prior chapter. So let's look at an example to help us kind of understand what's going on here. This relative frequency distribution represents the height of a pediatrician's 3-year-old female patients. Okay, the raw data indicates that the mean height, mu, equals 38.72 that's the average height of a 3-year-old female patient, with the standard deviation being 3.17 inches. Okay, these quote marks are a notation mark for inches, in case you didn't know that. Okay, draw a relative frequency histogram of the data and comment on the shape of the distribution. So if we take that relative frequency that we saw before in that table and just put it into a histogram, this is what you'd get here, okay? The figure shows that the relative frequency histogram is symmetric and bell-shaped. It's not perfectly symmetric, but it's roughly symmetric, increasing towards the middle, decreasing towards the ends. Draw a normal curve with inches on the relative frequency histogram and compare the area of the rectangle for heights between 40 and 40.9 inches to the area under the normal curve for 40.9. So you can see that rectangle here in green in the bottom diagram, and then you can see the curve, the normal curve that they wanted us to create, okay? Notice the area of this shaded region of the rectangle is almost the exact same as the shaded region. There's a little bit of the rectangle above the curve, and there's a little bit below the curve. So it's roughly, it's very close to the same area under the curve as it is in that rectangle. So we can use the area under the normal curve to approximate the proportion of 3-year-old females with heights between 40 and 40.9. Remember, that's when we do the area under the curve, we have two interpretations: the proportion of people who have the characteristic, or the probability that if I randomly pick someone, they would have that characteristic. Those two interpretations. The probability density function. The equation or model used to determine the probability of a continuous random variable is called a probability density function, or PDF. The normal probability density function is given by y equals 1 divided by sigma times the square root of 2 pi. All that quantity times Euler's constant raised to the power of negative the quantity of x minus mu, which is the mean, squared in the numerator, divided by 2 sigma squared in the denominator. Okay? So they've done it in a different version here too. You can also take the 1/2 out of the exponent of Euler's constant, as you can see, to the formula to the right. Don't feel threatened by this equation. We would not be using it in the text. Instead, we'll be using the normal distribution in graphical form by drawing the normal curve. Area under a normal curve. Suppose that a random variable x is normally distributed with the mean mu and a standard deviation sigma. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristic described by the interval, or the probability that a randomly selected individual from the population will have that characteristic. Okay, so when we looked at that between 40 and 40.9, we're saying that whatever that area is, it's the proportion of the population of 3-year-old females that are that tall. Or if we picked a random 3-year-old female, the area of that rectangle, the area under the curve would also equal the probability that a randomly selected individual would be at that height between 40 and 40.9. Interpreting area under a normal curve. So the serum total cholesterol for males 20 to 29 years old is approximately normally distributed, with the mean U equals 180 milligrams and standard deviation equals 36.2, based on data from the National Health and Nutrition Examination Survey. So the first thing we want to do is to draw a normal curve with the parameters labeled. So again, we know that the mean is 180, so that's the top here, okay? I don't know why I said the top. That's the center part, that's our center average value. The standard deviation is 36.2, so our inflection lines, our inflection points are at mu, mean plus 1 mu. 180 plus 36.2 gives us 216.2. And they're also at the mean, 180, minus 1 standard deviation, 36.2, and 180 minus 36.2 gives me that 143.8. And so again, these points, these inflection points, are where the curve changes from concave down to concave up. It's where the spoon flips over, if you will. Okay? An individual with total cholesterol greater than 200 milligrams is considered to have high cholesterol. Shade the region under the curve to the right of x equals 200. So we're somewhere between here and between 180 and 216. That's almost, 20 to 200, another 16. It's almost directly in the middle, but it's not quite. And so here is the graph with what we see is 200 and above. So the area under this curve from 200 up would represent the proportion of the population of males 20 to 29 who have high cholesterol, because that's what they're denoting 200 is high cholesterol. Okay. The last thing we're going to do is suppose that the area under the normal curve to the right of 200 is 0.2903. Provide two interpretations of this, which I kind of just did. So we know that about 29% of the population of males 20 to 29 years old has high cholesterol. That's really high, actually. That's almost 1/3 of young men have high cholesterol. Got to get away from those McDonald's meals, I'm guessing. Okay. And then we could also say that if we selected a person randomly, we have a 0.29 probability or a 29% probability that they have high cholesterol as well. Okay. And so that's the end of this section. It was a relatively quick one. Nice to know.